What if we took an ellipse and turned it inside out? It's a strange thought, and if it feels like the resulting graph would be divergent and infinite, you're correct. This is a hyperbola. It has the same foci as an ellipse, but instead of being defined by a fixed sum of distances to the foci, a point on a hyperbola has a fixed difference between its distances to the foci. A hyperbola is based on subtraction rather than addition. Here's a description. For any point P on a hyperbola, the difference in distance from P to the foci is a fixed value. And as with an ellipse, that value will be 2a. We'll talk about what a is in a minute. These two YouTube videos provide a way of visualizing the generation of a hyperbola. And if you're into connections, it is possible to generate all conics using these techniques. It's a worthy question to ask why. I will leave that as something for you to mull. Back to the origin. We will derive the equation of a hyperbola with center at the origin. The process is so similar to the derivation for an ellipse that we can actually skip some interior steps. Now, I've imported an image from the textbook, and we can use this to start building the distance relationships. Remember, we're working with a point on the curve, and the relationship that we know to be true, since this is a hyperbola, is that the difference between these two distances, in other words, this distance minus this distance, will be a fixed value. So let's look at this distance here first. Using our distance equation, distance formula, we should have x minus a negative c squared plus y minus 0 squared. And then we are subtracting this distance here. So that's going to be x minus c squared plus y minus 0 squared. And this is going to be equal to a fixed value. And I told you earlier that that was 2a. Now, this is the rather interesting fact. We are right now considering a point out here, but let's think about what we would have if we were talking about this point right here. For this point, the distance to the far focus would be right there. And the distance to the near focus would be right there. Now, note that this little chunk is the same as that chunk. So, if I subtract the small distance, the small green distance, so if I do, let's get the colors to match up. If I were to do blue minus green, what I'm going to get is simply the distance between the vertices. So blue minus green gives me that middle distance right there. And that is what we label 2a. That is to say, each of these distances is a. Okay, so now you know. That's where the 2a comes from. Let us forge ahead. Now, back up with this material. If we were dealing with an ellipse, we would have had a plus in the middle. Since we're dealing with a hyperbola, we have a minus. That means that all of the nasty crunching we did and the squaring and the foiling out is effectively the same operation, but with a change in negativity on one of the terms. And that presents a prime opportunity for a shortcut. If we go ahead and compress all of those steps, so we'll say same math as ellipse. If we compress those steps with the addition of the negative, we're going to wind up with the following result. We will have, when the dust settles, c squared minus a squared as a quantity times x squared minus a squared y squared equal to a squared times c squared minus a squared. Okay. Now, as with the ellipse, we will define a new value b squared that is the more cantankerous piece of this. C squared minus a squared is annoying, so we say let b squared equal c squared minus a squared. It will, of course, also correspond to the leg of a triangle. From there, we can say, well, that looks like b squared x squared minus a squared y squared equals a squared b squared. And if we go through and divide everything by a squared b squared, we wind up with x squared over a squared minus y squared over b squared equals 1. And that, my friends, is the equation of a horizontally oriented hyperbola. Now, we already said that hyperbolas are all about subtraction. For the standard equation of a hyperbola, the value of a will always be the denominator of the positive term. Positive term. So this is a horizontally oriented hyperbola, thus the a value is under the x, and we know that whatever was the positive term will have the a value. Now, a horizontal hyperbola, the equation of a hyperbola with center at the origin and a horizontal transverse axis. That's a little bit of a new word. Think of it in the same way as the major axis with a ellipse. So a horizontal transverse axis has the following properties. Our equation is what we derived up above. The vertices, as with an ellipse, are located at plus or minus a and 0. The foci are located at plus or minus c and 0. And here's a distinct difference. We have c squared equals a squared plus b squared. So c squared is the largest value for a hyperbola. In an ellipse, remember, that was a squared. Okay, we also have a transverse axis that behaves the same as the major axis of an ellipse. It's got length 2a. And another new feature, we have asymptotes. Yeah, we'll talk about those more. Let's look at how these things play out in a sketch. So I've pulled in a figure that already has a and negative a marked out, along with b and negative b. Now, it's important to know where b and negative b are, but we won't actually keep points on them. A and negative a are in fact the vertices. Remember, we're looking at those over there. So there we go. The foci land at c squared, which is a squared plus b squared. And those are going to exist roughly right about there and there. So we'll say that that is c and that is negative c. Now, the reason that I've drawn in this grid is because this rectangle is the most effective way to sketch the graph of a hyperbola. It shows us the asymptotes of a hyperbola, and this is the very new facet of this type of graph, the idea that because it's diverging to infinity, we actually have two lines which are approached as x goes to infinity. The book gives a good derivation that proves how b over a times x is the limit as x goes to infinity when you're looking at this thing. We're not going to dig into it right now. For our purposes, you should know that when you're sketching the graph of a hyperbola, these asymptotes are the most surefire way to create an accurate image, and you will need to draw them every time we generate the sketch of a hyperbola's graph. Now, we just did a horizontally oriented hyperbola. Of course, we can orient the hyperbola vertically as well. And a vertical hyperbola simply has the a value under the y squared. That is to say, the y squared over a squared is the positive term. Vertices shift for a to be now a y, same with the foci. Our relationship here holds, as does the transverse axis. There is a change in the asymptote. A is now on top. Formerly, A was on the bottom. Let's just go back and look at that again. Yeah, we see that right there. So that's something to keep in mind. Your asymptotes always have a slope that is rise over run. In the case of a vertically oriented hyperbola, A is describing rise. So let's practice sketching so you can see how we would build this out in absence of all the pre-made material. First, I'm going to mark in my A values. So we'll say there's A, there's negative A. Say that those are my B values. Okay, and then I'm going to do the box. Okay. And the asymptotes, my asymptotes we said were plus and minus a over bx. So y equals a over bx, that is going to be this line. And it should be passing through the origin, right? That's a failing in my drawing. Now we will also have as another asymptote y equals negative a over bx. And that line will be passing like so. If I can get a non-shaky, there we go. Okay. Okay, now the asymptotes help define the end behavior of, or not help to, the asymptotes do define the end behavior of the hyperbola. So we then sketch in starting from A and just let our lines be drawn into the asymptotes. Okay, and there we go. That is how you approach sketching the graph. Let's move into finding the equation of the hyperbola with vertices plus minus 3, 0 and plus minus 4, 0. clear this up a little bit. Okay, so vertices at plus minus 3 and foci at plus minus 4. Well, let's go back and check ourselves. If it's vertex on the x-axis, that is horizontal. That is this sucker right here. Okay, so we can see immediately, okay, horizontally oriented. Okay. We then have the a value, right? The a value is the vertex. So you know that a equals 3. The foci are at plus minus 4, 0. So that means that c is equal to 4. Okay, so now we need to find a b value. We have that b squared equals c squared minus a squared. So that's going to give us 16 minus 9, which is 7. B squared equals 7. Okay, and let's double check ourselves again. We said we were horizontally oriented. So this will be an x squared over a squared minus y squared over b squared proposition. So we'll have x squared over a squared, which is 9, plus y squared over, well, b squared is 7. So I don't even need to worry about taking that square root. I'll just put in the 7. And we're equal to 1. That's all we needed to do there. That's great. Awesome. Okay, now, number 2, sketch the graph of the hyperbola above. Okay, well, let's recall what we did just before. We said we needed a few things to build a sketch. We needed A, B, and we needed the asymptotes. Okay, which were of the form y equals plus or minus. This was horizontally oriented, so which goes on top? Does A or B go on top for horizontally oriented? Yeah, B goes on top. Okay, so it'd be B over A x. These are the pieces we need. Fine, we've got that. We know from right here that A equals 3. We've got that. Well, this time we'll have to take a square root, right? B equals root 7. That should do it for us. This is funny, right? We don't need C actually at all to do the sketch. Just needed to find B. Okay. And remembering again, we are horizontally oriented. We know that. So A, 1, 2, 3, 1, 1, 2, 3. B is root 7. Now root 7 is going to be slightly less than 3. So we'll go 1, 2, 3, 1, 2, 3. And we'll just drop a point somewhere in there for B. We'll push out to here and note that that's A. Negative A. My negative x is a little broader. That might produce some uglies in a minute here. Now let's build our box. Okay. Got the box. We know that we are dealing with the lines y equals plus or minus root 7 over 3x, but we don't even have to calculate that or sketch it independently. We can simply use the corners, right? We can use these 2 points on our box, and we know that our asymptotes are going to cut through both corners. So we'll just go fire away. Try that again. Third time, yes. Great. Again, centering, always a challenge. Okay, horizontally oriented. That's why I labeled my A's specifically, A and A, because I don't want to forget at the last minute and end up sketching in a parabola vertically when in fact, or said parabola, sketching in a hyperbola vertically when in fact it should have been horizontal. And there we go. That's good enough. That is a perfectly acceptable sketch for our purposes. Now, this time a slightly different challenge. Given the equation x squared minus 9y squared plus 9 equals 0, find the vertices, foci, and asymptotes, and then also sketch the graph, so the whole tamale. But we are starting out with an equation that is not in standard form. So the first step is to get standard form, get standardized. That means pushing the 9 over to the other side and then dividing both sides by that negative. So we're going to have negative x squared over, that's not, negative x squared over 9 plus y squared equals 1. Ew. Now this is interesting. This is interesting. We're going to need to do some reshuffling here. And it would be to our benefit to add a 1 below that y squared. Okay, we'll put the x squared over 9 second with the negative. This tells us that this particular hyperbola is vertically oriented. And it highlights an interesting fact. This value is bigger than this one, but the 9 had the negative on it, so it's not A. 9 is B. So 9 is B squared. 1 is A squared. And we're going to use those. So we need to find vertices, we need to find foci, and we need to find the asymptotes. So we have that our vertices are going to be 0 on the x, because this is vertically oriented, and they're going to be plus or minus 1 on the y. Our foci, well, we know that b squared equals c squared minus a squared, so that implies that c squared equals a squared plus b squared, so c squared must equal 1 plus 9, and c equals root 10. So my foci are in the same, they're oriented along the same axis as my vertices, so foci will be 0 plus or minus root 10, so substantially in from the vertices. And then the last piece we had was asymptotes. Okay, so for my asymptotes, those are going to be y equals, and this time, what goes on top? We are vertically oriented, so vertically oriented means, yeah, A goes on top for the asymptotes. Okay, so y equals plus or minus A. A is 1 over B. B is 3, so 1/3 x. Okay, and so with that, we should be good to sketch. Let's give it a whirl. So root 10 plus or minus root 10, that's slightly bigger than 3. 1, 2, 3, 2, 3, 4. And we knew that B was 3, so 1, 2, 1, 2. So there's little placeholders. Remember again, the important things to get on the board are our A values. Okay, and then also we will be using our B values at 3. So I'm sketching my box. Okay. So remember that right there. That was B. That was negative B. Okay, let's get some asymptotes in. And again, and now, remember it's vertically oriented. That's where the A is. So very shallow. And that would be a sketch. Last challenge, find the equation and foci of a hyperbola with vertices 0 plus or minus 2 and asymptotes y equals plus or minus 2x. Sketch the graph. Okay, now remember that our vertices are given as 0 plus or minus a. So this is wholesale handing us the a value. We can say from here that a equals 2. And then we need to take a look at our other information to see what else can we find. We know we need to find B, we need to find C, and if we get those two, we should be able to move onward. Now, plus or minus 2 on the y means that this is, we know that this is vertically oriented. Okay. Now let's think about what else we can do if we know that it's vertically oriented. Well, if we know that it's vertically oriented, that means that my asymptotes must have had the form y equals a over b, plus or minus a over b, x. And conveniently in this case, we know that the asymptotes are plus or minus 2x. So the implication here is that since we know that a is 2 and that we've got a 2 right there, this means that b must equal 1. Okay. Now we also need to define c. So let's work on that. C squared equals a squared plus b squared. So we'll say that c squared is equal to 4 plus 1. That is to say c squared equals 5. So we can pull that sucker up and say c itself must be root 5. Okay, this gives us enough to find the rest of our information. We're supposed to find the foci, right? We know that the foci are going to be the same orientation as the vertices, so we'll do a 0, comma, and then we'll use our C value, plus or minus root 5. Okay, and then the last piece of this is to get the equation, and that's not going to be hard. We are vertically oriented. So a vertical orientation, let's go back up and check out what else was going on here. Vertical orientation means that y squared is the positive term. So we'll have y squared over a squared minus x squared over b squared equals 1. And we knew that a was 2, so a squared is 4. We know that b is 1, so b squared is still 1. And that's it. That's a really solid equation. We are done with that part. We're still supposed to sketch, so we'll move this up and out of the way. Get after sketching this graph. Okay. So my A is 2, my B is 1. C doesn't really have an impact when we're sketching. Life lessons, 1, 2. B is 1, 1. Go down 1, 2. So I've got A, I've got negative A, I've got B, I've got negative B. Let's draw my box. And draw my asymptotes. Connect the corners of the box. Okay, now again, I'm vertically oriented. This is the point where you always have to ask yourself, which side am I filling in? Am I filling in here? No, I'm not. That would be horizontally oriented. I'm vertically oriented. So that means that I am filling in up here. So let's define our vertex point and then carry on with sketching in. Vertex point. And there we go. You can always check these graphs using Desmos or your graphing utility of choice. Desmos does a nice job because you can actually enter in y squared minus x squared with their coefficients as written. You don't have to do any further manipulation. And it is a valuable thing to check your work. Do one of these where you're supposed to graph it by hand, get your sketch in place, but then do go back and check yourself with Desmos.